Hello student, welcome to the next chapter of our third unit, which is the last chapter, magnetism. Some basic definitions and one important topic. So here we will discuss first some important terms connected with the magnetism. First is magnetic field. It is a space around a magnet in which its magnetic influence can be felt. So when a magnet is present, it creates its magnetic field around itself, which can be experienced with the help of another magnet when brought in this magnetic field. Uniform magnetic field, a field which has same strength and same direction in a certain region of the space, we call that as the uniform magnetic field. Magnetic poles, regions of the concentrated magnetic strength in a magnet, they are known as the magnetic poles. So if we draw a magnet like this, then near their physical ends we can find these points shown by the dot, where magnetic north and magnetic south poles are present. You can easily find them on a actual bar magnet. You just have to sprinkle a fine iron powder over the bar magnet. You will see that maximum density of the iron powder will not be at the physical end, but little bit on the interior side of the physical end, where you will get the maximum iron powder particles attached with the bar magnet near the physical end. That will be the magnetic pole. Next is magnetic axis, a line which is passing through the two poles of a bar magnet, that is called as the magnetic axis. Magnetic equator, if we draw a line which is perpendicular to the magnetic axis from the center of the magnet, we call that as the magnetic equator. Magnetic length, the distance between the poles of a magnet, we call that as a magnetic length. Distance between the physical ends of a magnet, we call it as the geometric length. And this is an important relation between the two lengths, that magnetic length is always 0.84 times the geometric length. So if we draw a bar magnet like this, this will be the magnetic, say, north pole, this is the magnetic south pole. So a line which is passed through along the length of the magnet, which connects the two poles, we call that as the magnetic axis. The origin of the center of the bar magnet is the center of the line joining the two poles, north and the south pole. So if we pass a line perpendicular to this, we call it as the magnetic equator. If we indicate the distance between the north to the south pole, this much distance from north to the south pole, we call it as the magnetic length. Whereas if we find the total distance from one physical end of the magnet to the other physical end, we call it as the geometric length. Next is Coulomb's law of magnetism. This law states that if we have two magnetic poles with pole strength m1 and pole strength m2, and they are separated by a distance r, and they are present in a vacuum or free space, then law says that the force of attraction or repulsion between the two magnetic poles is directly proportional to product of their pole strength and is inversely proportional to the square of the distance between them. That is, F is proportional to m1 m2 and is inversely proportional to r square. So if we combine them, F is equal to constant proportionality K into m1 m2 divided by r square. Okay. Now this constant proportionality K in SI system is equal to mu naught over 4 pi in SI system. Therefore the F will be equal to mu naught over 4 pi into m1 m2 divided by r square. This is the expression for Coulomb's law in magnetism. Okay, it is a Coulomb analog of the magnetism. We already know that mu naught is the permeability of the free space, which is equal to 4 pi into 10 raised to power minus 7 Henry per meter. H is Henry, another unit, alternate unit of the permeability, about which we will learn in the next unit. Now definition of the unit pole. If M1, M2 both are equal to 1 unit and R is equal to 1 meter, that is both poles are of the unit strength and separated by distance 1 meter, in that case if we substitute these values in this equation, F becomes equal to mu naught over 4 pi, which is nothing but 10 raised to power minus 7 Newton. So from here we can define a unit pole as that pole which when placed in vacuum at a distance of 1 meter from a similar pole, it will repel it with a force of 10 raised to power minus 7 Newton. So just like we had defined 1 Coulomb, one pole, unit magnetic pole is that pole which when placed in vacuum at a distance of 1 meter from an identical pole, it will repel that with the force of 10 raised to power minus 7 Newton. Next is magnetic dipole. A bar magnet is a magnetic dipole. Magnetic dipole means two poles of same strength but of opposite nature separated by a certain distance. So just like we have electric dipole, combination of two equal and opposite charges, we have a magnetic dipole. So our bar magnet is nothing but a magnetic dipole which has two poles, north pole and the south pole, which are of the same strength but separated by a distance called magnetic length. We can define its magnetic dipole moment as the product of pole strength and the magnetic length, which is indicated by letter small m, which is equal to m into 2L, which is equal to m into 2L. We represent it with capital M, and its direction is from, and it is directed from south to the north pole. Remember its direction. It's a very important 1 mark question. SI unit. SI unit of the magnetic dipole moment is ampere per meter square or joule per Tesla. So we can either use ampere per meter square or we can also use joule per Tesla. Next is magnetic field lines. We have already studied in the lower classes that a magnetic field line is a curve tangent to which at any point on the line gives the direction of the magnetic field at that point. Okay, this means that if this is the magnetic field line, which is a curve, and we want to find out the direction of magnetic field at this point, what we need to do, we will just draw a tangent which will touch the field line at this particular point, and this arrow will represent the direction of the field only at that point. Field lines in the most of the cases they are curved, but only under certain circumstances they can be directed in straight line, especially in the uniform magnetic field. Otherwise they will be curved in nature. Important properties of the field lines. Field lines, they are always closed curves. If you remember, you had drawn the magnetic field lines in the lower classes for a bar magnet. You have drawn them like this. If this is the north pole, this is the south pole, you have drawn them like this. Outside the bar magnet, they are moving from the north to the south pole, but in the interior of the bar magnet, they are running from the south to the north pole. That means they are always closed curves. Two field lines do not touch or cross each other. Reason? Its definition. If we have two field lines, this one and this one, and they intersect at this one particular point, Then in order to know the direction of magnetic field at this point of intersection, we can draw two tangents, one directed along this field line, another directed along this field line. It indicates that a magnetic field, a single magnetic field at a single point possesses two different directions, which is not possible. So they cannot touch or even cross each other. Field lines are always closed curves, so they do not have any starting point or they do not have any terminating point. But important thing, they will always be normal to the surface of the magnet. Just like electric field lines are always normal to the surface of a conductor or the charge, magnetic field lines are always normal to the surface of a magnet. Relative closeness of the field lines gives idea about the strength. So if in a certain region magnetic field lines are close, then field is strong there, but if in certain region they are far away, their field strength is weak. So you can see that a point lying over here A, the field strength is strong because field lines are close to each other, but if a point B, the field lines are weak because they are away from each other. So in this way we can find out the strength of the magnetic field just by looking at the magnetic field lines.